at least my goal is to present sort of a bunch of theoretical background for something called finite entanglement scaling, but ultimately the choice of what I'm going to present is motivated by numerical considerations, and roughly the question is, if you want to extract properties of conformal field theory, either in 1D or maybe 2D, how would you do it using the density matrix renormalization group? And in particular, the point of view I'm fond of is the infinite density matrix renormalization group, where you're able to use translation invariance to directly take the thermodynamic limit at the very start. So whereas in usual finite size numerics, like if you're doing exact diagonalization or finite DMRG, the way you would approach critical phenomena is with finite size scaling. But in this case, the size is already infinite because you're going to be working in the thermodynamic limit. So the question is, what's the analog of finite size scaling when using IDMRG? And I think there's a really beautiful, so the main result I'm actually presenting is due to Frank Pullman, Subroto, Ari Turner, and Joel Moore. So that's this paper here. And I think it's a really beautiful result that not that many people know. So I actually want to spend the time to give you the background in entanglement and 1D CFTs so that you can derive how this works. And then if I have time, which I might not, I'll try and discuss what might be more modern application of it, which is how you would use this finite entanglement scaling to extract properties of non-Fermi liquids in 2 dimensions. So to be able to see the emergence of a Fermi surface using DMRG numerics. OK, so probably a lot of you are already familiar with entanglement, but I should at least define it. So I'm going to draw my pictures as if I'm in 1D. So suppose this is my 1D system here. And the basic starting point of entanglement is to split your system into 2 regions. So I'll call it B is the center region here, and A is the region here. So the Hilbert space then, H, you can think of as being a tensor product between the degrees of freedom in region A and the degrees of freedom in region B. And I can imagine that I have some quantum state, a pure state psi, living in the entire Hilbert space here. OK, so the definition of entanglement is it's a property of a state, but not just a state. It's a property of a state and a cut of the system into 2 subregions, so A and B here. So then what I do is I consider the reduced density matrix, RDM for the system, which is defined by forming the density matrix for the pure state, which is kind of trivial here, and then tracing out the part of the system I'm not interested in. So in this case, this is row A, and this defines the reduced density matrix on B. And the useful thing about B is it's a density matrix, like we're familiar with for mixed states, that contains all possible information about observables if those observables are contained only in B. Meaning if I wanted to know, for instance, the expectation value of a 1-point function localized in region B, using this definition here, you can see that that's the usual way you would get a expectation value from the reduced density matrix. OK, so entanglement comes about in the following way. We started with a pure state, but by tracing out A, I get a mixed state on region B. And entanglement is just what is the entropy of that mixed state, right? So if A and B weren't talking with each other, you'd find that the reduced density matrix for B is still actually a pure state. But if there's quantum fluctuations across the cut here, then B ends up being mixed. So the way to quantify this is I can imagine taking the reduced density matrix and then diagonalizing it. So this is a sum over eigenvalues J. Now, each of these is a positive weight. So call this Pj greater than or equal to 0. They sum up to 1. That's just that the norm of the density matrix is 1. It has trace 1. And because they're all positive, some people like to rewrite this by imagining that it actually comes from some fictitious energy spectrum. So you can call it EJ. And then this spectrum of coefficients here is the entanglement spectrum. At least it was named this by Duncan Haldane in 2008, but people had been studying this spectrum decades before in quantum information. OK, and then the entanglement entropy is we can treat this as a probability distribution and compute the usual von Neumann distribution SB is equal to sum of the values Pj log Pj. Okay. So it's a property of region B. What's the best way to do this? Okay, so that's the von Neumann entropy. But actually for CFTs, it's a little bit more convenient to work with a different type of entropy called the Rényi entropy. So what I'm going to define is something I'm going to call, this is just a notation here, Z of n of region B is going to be you find these eigenvalues of the reduced density matrix and then sum them all up, but raised to the power of n. So this gives you some number less than 1, because each of the pj's is less than 1. And the way it encodes entanglement is basically big Z means small entanglement and vice versa. And the reason is simply, in a system with a lot of entanglement, it means there's a large number of these pj's which have non-zero weight, so they become small. And because you're taking a small number and raising it to a power, Z gets small. The relation to the Rényi entropies, just by definition, is that the nth Rényi entropy of region B is defined to be log of Z over 1 minus n. But for our purposes, it will actually be more convenient to work with Z rather than log of Z. N here, so it's basically a sequence of different entropy measures. So usually n is any particular integer going from 1, 2, 3, 4, 5. And this is the nth Rényi entropy. So it's a sequence of different entropy measurements. It turns out that this von Neumann one can be extracted as the limit of this as n goes to 1. But more generally, you could look at n equals 2 or 3. Yeah. Yeah, this is the definition of Z. So I mean, I could rewrite this as just being you take the reduced density matrix, rho B, and raise it to the nth power.
So n can also be fractional?
From this definition here, yeah, n could be fractional. Yeah. So there's some special cases, like if you take, for instance, if you take n goes to 0, that's called the rank of the reduced density matrix. Because if you take n goes to 0, you're raising these numbers to the 0th power, and it's actually just counting how many non-zero eigenvalues are there. So the 0th Rényi entropy is calculating the rank of the reduced density matrix. Another limit is when n goes to infinity, the largest term here is going to dominate over all others. So that tells you something about simply what's the largest eigenvalue in the density matrix. And the limit n goes to 1, you can use to recover the von Neumann entropy. Oh, actually, I should. OK, so I want to discuss how these, sorry, I erased that. What these behave like in gapped and gapless systems. So first, let's say I have a 1D system with a mass gap. And what I could look at quantitatively is I cut it into this region B. Let's say this has size L. I could make a plot of what this Zn looks like as a function of L, or so do we have other colors here? No. So if you look at what Zn looks like, so we said big Zn means little entanglement. Small Zn means a lot of entanglement. And what you tend to find is, let's say this is the size of the region I cut out here. It will do something like this. So a small region won't have too much entanglement. As you make the region L bigger, it has more entanglement with the rest of the system. So for this funny measure here, it means that Z goes down. But the important thing is that as L gets really big, this doesn't keep going down to 0. Instead, it actually saturates at a finite value. So a more familiar way of putting this is in terms of the von Neumann entropy VB, in which case this graph would look something like this. And again, the amount of entanglement would saturate as L becomes very large. So this is the so-called area law, that even though B can get really big and has a lot of degrees of freedom, if it's gapped, not all of those degrees of freedom can be entangled with A. And the reason it's called the area law, it's a little bit trivial in 1D, but it's more interesting in 2D. If I played the same game in 2D, I could cut out A to be a subregion here and B here. Actually, sorry, B here and A here, and ask what's the entanglement of the region B with the rest of the system. And what you would find is this scales as some constant times the perimeter of B. This is the perimeter. So that's why people usually call this the area law, which is that the entanglement between two regions scales as the area, the boundary between them, not as the volume of the region. Now in 1D, if you ask what is the perimeter or the boundary between the two regions, it's zero-dimensional. It's only 2 points. So in this case, it just saturates to a constant. Yeah.
Until size of space infinite, A is infinite.
Yeah. This saturation would be true even if A was very large and finite. Though the difference if, let's say it did end right here, and I repeat this experiment, eventually B starts getting bigger than A, and this would actually come back down. Because it turns out that for pure states, by the definition of the entanglement entropy, the entropy of A is the same as the entropy of B. So it actually has to come back down in the case where this is finite. Good question.
What
Yep.
kind of symmetries are we assuming for models like translation symmetry
This,
one-dimensional?
you mean in order to get an area law? Yeah, so we're assuming, okay, well, so it's a little bit hard to phrase the area law if you consider a system with disorder. Simply because you could do perverse things where if the system is very inhomogeneous, like you imagine taking the gap to 0 or something as you go out to infinity, then it becomes hard to phrase this. But if there's some notion of it being homogeneous, then any region will have an area law. Now what you are assuming is that it's gapped and that the interactions are local rather than some perverse power law.
And it's only true for ground state, right?
Yeah, this is true for the ground state. So exactly what happens if you're at finite energy density. So at finite energy density, your state effectively looks thermal. And then rather than having this area law, when you compute S of B, you're actually calculating something equivalent to the thermal entropy, which satisfies a volume law. Like usually if you have a density matrix on system B at finite temperature or energy density, the entropy in here is an extensive, meaning the volume law. So that's why this area law is special to ground states. Okay, so in 1D, this is actually proven by Hastings and other, the existence of this saturation in the area law. But it's interesting to ask, what if the gap is 0? So meaning it's, say, conformal field theory. How does the entropy then depend on L here? So conformal field theories make it, there's a beautiful way to calculate entanglement properties in conformal field theories by placing them on higher genus Riemann surfaces. So there's a really beautiful technology there. But the way to think about the end result is pretty simple. So whenever you cut out a region, there's a set of points at the boundary between them. So here, because I just have A, B, A, there's only 2 points at the boundaries. But I could do more fancy cuts where it was 2 intervals, like A, B, A, B, A, and then I'd have 4 points. But you can see always in 1D, when you calculate entanglements, you have a series of points associated with boundaries. And so what you find for, this is why I chose to define Zn, it's a little more convenient here, is I can calculate the entanglement n, let me do the 2-point case, associated with cutting out this region here, x1, x2. And you find it goes like some constant, f of n, x1 minus x2 to the negative c over 6 n minus 1 over n. Or maybe let me write this a little bit more suggestively, f of n over x1 minus x2 to the 2 delta of n, where this exponent delta of n is defined to be c over 12. So I'm not going to derive that this is true, but we see it takes a very nice form. These 2 points, the amount of entanglement is measured by Zn, follows this power law form here. Now remember I said that when Zn gets small, that means there's more entanglement. So you can see as I take these points to be far apart, Zn is increasing, meaning the entanglement between B and the rest of the system is increasing. And now, unlike the gap case, as I take this region to be very large, this decays all the way to 0, meaning that the entanglement is actually diverging. So sometimes you'll hear people call this the logarithmic divergence in entanglement. Now this suggests actually that, what are other things that take the form of power laws? Well, in general, if you have a critical point, a conformal field theory, and you calculate a 2-point function of 2 observables, like scaling observables, it goes as a power law, where the power law depends on the critical exponents. So this form seems to suggest that the endpoints of entanglement cuts behave like scaling operators in a conformal field theory, with this peculiar exponent here that depends on the type of entanglement measured, the Renyi index, and c, where this constant c here is the central charge of the CFT. So this is a number that can be associated to any critical point in 1D, and basically it calculates the heat capacity of the system at low temperatures. So large C occurs in systems with a lot of the degrees of freedom, so it has large heat capacity. Small c for systems with a smaller number of degrees of freedom. So this tells us that entanglement, the amount of entanglement in a region, is determined by this central charge. So the nice thing about this is that it lets you constrain, even if I make a more complicated entanglement cut with, say, x1, x2, x3, x4, it won't necessarily exactly be this particular simple power law, but knowing that each of these points behaves like a scaling function means that all the usual technology of CFTs for letting you calculate 2, 3, 4-point functions can be applied to entanglement as well. Yeah?
Can we outline this strategy to compute this VN?
Yeah, I don't want to spend too much time on it, but roughly speaking, what you're doing is you're trying to calculate the trace. Let's say I do Z2. You're trying to calculate the trace of rho b squared by definition. So you can first ask in an imaginary time formalism, what does rho b look like? So let's say this is the imaginary time tau. We know that the way you would, so first suppose I want to prepare the ground state psi. the way you prepare a ground state in a conformal field theory is you do the imaginary time path integral from negative imaginary time up to tau equals 0. And then you put a cut in your path integral in order to generate the state. So I'm going to be very schematic here. Now, what tracing out B corresponds to is gluing together the path integral over region A, but leaving B still with a cut. So I'm going to be kind of schematic. So this gives you a path integral representation of the reduced density matrix. And then taking powers of this, you can show as a geometric interpretation of gluing together different sheets of the imaginary time path integral into something that's actually a higher genus surface. I don't think I can get into it with the level of detail, just so I can get to the other topics. But I could discuss that more after. Yeah?
So for large n, the exponential is n, not big n, right? Because where n is small. So do you have any comment about this behavior at large n?
Well, I think so. At large n, yeah. So so this was showing up from pj the n. So you can say as n goes to infinity, this is actually going to limit to the large. Let's say I order these, so p0 is the biggest one. As n goes to infinity, this limits to this form. So this is actually this limit here is telling you something about the scaling of p0, the dominant one. Basically, that it goes as a logarithm in actually, no, sorry, p0 goes as a power law in the distance L. Yeah?
So what if region B is a two-dimensional surface taken out of a three-dimensional system? Basically, I mean, A and B are of different dimensions. They are one dimension different.
So that, could I ask this question in 2D? Like, suppose I had a 2D conformal field theory and I cut it like this, ABA? Is that equivalent to what you're asking?
If the entire system is three-dimensional, while region B is a two-dimensional surface.
I see. That actually won't quite make sense because well, it depends. Okay, so if you go back to the starting point of the entanglement, you're taking the full Hilbert space and decomposing it into A and B. Yeah. Now, I mean, you could choose your B to be a volume that's kind of thin, so it's membrane-like, and ask about the properties of that. But usually, if you take any region which has one dimension which is really small, then there's not going to be very much universal about it because it's going to be sensitive to lattice effects. So generally, to get any universality out of these things, you need the size of the regions to be becoming big.
Sorry, this comment about boundaries, did you mean that they behave as a primary field because of this scaling?
Yeah, as a scaling operator or primary field, yeah. So they actually behave like primaries. Mm-hmm. So that means for like a 2-point function, that uniquely fixes it. For a 4-point function, like if you're familiar with CFTs, there's some ambiguity. And there's actually interesting results, like you can uniquely predict it in the case of large N CFTs and so on for what the 4-point functions are for entanglement. Yeah. But in general, two interval entanglements aren't that trivial to calculate except for the scaling constraints on them. The other nice thing about this is I'm doing it for a pure state, but you can ask, okay, so what's useful about knowing it's a scaling operator or a primary? Let me do another geometry, which would be rather than doing an infinite system, I'm just going to do an open chain. Sorry, I should stop erasing. So let's say you have a critical system, but it's on a strip, just meaning it has finite boundary conditions here. Now a different type of cut I could do is A and B, and let's make this size L and this size L minus L. So L is the total size of the system, and I can ask what is Zn, region B, which now depends on two parameters, L and L minus L. But actually, I'm going to write it as L and L over L. So now in this case, this is like a one-point function, because I've only inserted this cut. There's only one of them. So we know now that this has to have the form of a scaling collapse of the following form. This needs to look like L to the negative delta of n times Z n 1 L over L. So this is the usual way that you can do scaling collapses. I have this object has definite scaling dimension. It has scaling dimension delta n because it only comes from one cut, one point. It's a function of something that has dimensions of length and something dimensionless. So you can do a usual scaling transformation by rescaling everything by big L. That sets this to 1, but then you pick up a factor of the scaling dimensions here. OK, so even if you don't know how to compute this thing, it immediately tells you that if you fix where you do the entanglement cut to be some particular ratio of little l over big L, and then take the system size to be bigger and bigger, and compute that entanglement, you're going to see it's going to follow a power law with this exponent delta of n. And as I said, delta n is equal to c over 12 n minus 1 over n. So by looking at the scaling of the entanglement here, you can extract the central charge. So that's very useful from the point of view numerics, because what this is saying is central charge usually you often think about as being a thermodynamic property. For instance, one way you could measure it is by measuring the heat capacity of something. But a lot of the numerics that we can do, like DMRG, it's not easy to get lots of excited states, but it is easy to get the ground state. So this is giving you a way to compute central charge just from a ground state. Now I can actually tell you what the form of this here is, because it's kind of useful. This is actually L negative delta n sine pi L over L to the same negative delta n. So if you were to plot this, Zn L over L, it does something like this, according to that functional form there. So this actually gives a pretty accurate way to extract the central charge from finite size numerics. But one problem with this is, when I write this, this is in a scaling regime where implicitly the size of everything has to be very large compared to the lattice scale. And in general, to enter that scaling regime, you might need factors of many hundreds of the total system size compared to whatever your lattice scale is to enter the scaling regime. And for some systems, you certainly won't be able to use exact diagonalization to get into that regime. And even DMRG becomes hard simply because as you make the size of the system larger and larger, the amount of memory and so on goes linearly in the size of the system. In 1D, I'm not sure you would usually really encounter a problem, but because eventually I want to apply this to two-dimensional systems, it's easy to envision systems like systems I've dealt with where doing the finite case would actually be very difficult just because of the memory requirements. So now I want to discuss kind of what the analog of this is if you're going to do DMRG in the thermodynamic limit. OK, so I don't actually want to discuss what the DMRG algorithm is. But I want to give a succinct definition of it in terms of entanglement properties. So DMRG is a variational method. So I need to tell you what the variational class is. And once you know what the variational class is, the algorithm just works by minimizing energy within that variational class. So the variational class are the so-called matrix product states. And I'll write a particular matrix product state as chi, where this is an integer, which is the so-called bond dimension of the matrix product state. And matrix product states are really defined by the following property. They're one-dimensional states, and if you cut out a region B, you will always find that if you were to calculate the reduced density matrix for region B, no more than chi-squared eigenvalues will show up. Or there's an equivalent way to do it, which is if you had a system like this, AB, and I compute row B, then exactly chi eigenvalues will show up. And this will be true even as you take the system size to infinity. So these are very special because generically, when you look at these density matrices, the pj decrease in magnitude for large j, but generically there's still an infinite number of them. Matrix product states are very special because when you're looking with a bond dimension chi matrix product state, there will be no more than chi eigenvalues in the density matrix. And if you massage this definition a little bit and ensure that this is true for any particular entanglement cut, that's actually equivalent to the definition of matrix product states in terms of tensors and so on. But conceptually, I'd like you to think about it this way. It's the variational class in which any entanglement cut has no more than chi non-zero entanglement eigenvalues.
So it's already zero, or just ignoring them?
Well, this is the special variational class, so like a subset of the full Hilbert space where they're truly zero. Yeah. So it's a restriction on all possible states. Like, if this is the full Hilbert space associated with, a 100-site chain, the states which have this property that the entanglement is, or that these eigenvalues are exactly zero after chi is some very little space here. So let's say this is chi. But if you go to larger and larger chi, of course, that's less and less restrictive. So as you increase chi, you're going to start covering more and more of the total space.
So for generic state in a 1D-depth system, then there should be like more non-zero coefficient.
Yeah. So generically, there's actually an infinite number. They just fall off. I'll actually discuss quantitatively how these PJs fall off, because the rate at which they fall off is telling you what sort of errors you make by approximating states by matrix product states. So another way to summarize this actually is just like if you have a chi-sided dice, it can't have more than log chi entropy. For these matrix product states, if you were to calculate the entanglement SB of a region, it's bounded from above by log chi. So for gap states, this will generally work pretty well because we said even if you take really big regions, the entanglement in a gap state saturates to a constant. So that suggests that as long as you choose the so-called bond dimension to be large enough, once log chi is sufficiently big compared to whatever that saturated value of the entanglement entropy is, then you're going to be able to capture the state efficiently with a matrix product state. And Hastings has a formalism of this, or like a way to formalize this, that there's a very precise mathematical sense in which gap states are accurately, can be accurately captured as matrix product states. But we know from this actually that this naively won't work very well for conformal field theory. for the conformal field theory, the gapless point we said is you take the size of a region B to be big, the entanglement actually grows without bounds, because of that power law form. So that's telling you, but on the other hand, the matrix product state, the amount of entanglement is bounded. So it means something is going to go wrong if you try and approximate a critical state with a matrix product state. So, you may hear then that DMRG doesn't work for critical states. But the very interesting question, which was raised by, in this paper by Pullman et al., was, okay, well, suppose you just do it anyways. Suppose you're given a Hamiltonian at a critical point, and you just run DMRG with fixed bond dimension chi to get the best approximation of the ground state that you can. What are the properties of that matrix product state that you're optimizing?
So what do you mean by the lowest energy?
Yeah. So, oh, sorry, I sort of skipped something here. So what DMRG does, so matrix product states, this is the variational space. What DMRG does is it minimizes over all states, a bond dimension at most chi, the expectation value of the Hamiltonian. So this is just usual variational principle. Given a variational class, if you minimize the energy, you're going to get the best approximation of the ground state within that variational class. And DMRG is just an efficient and fancy way of doing this minimization problem. The time it takes scales as some polynomial in chi cubed, actually. And of course, as chi increases, you have a larger and larger variational space, and you can get a more accurate approximation to the ground state. So when I say minimize the energy, I just mean minimize the energy of the true Hamiltonian within this restricted variational space. Yeah.
So I'm just a little confused because you're saying we're picking a chi, but that's going to bound our entropy, so you have to pick a large enough chi to.
Yeah. So what you would tend to find is, so let me call this thing E of chi. It's the best energy that you could get within that variational space. You could ask, let's say it was a gap state, you could ask, how does E of chi behave as a function of chi? And it will do something like this. Let's say the true ground state energy is this dotted line here. For finite chi, you can't get the exact ground state, so the energy is higher by some amount. But then if you're willing to spend more and more time, according to this O chi cubed, you can get a lower and lower energy and therefore a better approximation of the ground state. This fall off here is generally some power law in chi. People pretend it's 1 over chi, but it's not. It's some other power law.
Well, that's only true if we always, for every chi, we pick the ground state, right?
What exactly? Yeah. So what I'm saying is, pick a chi, and then solve this variational minimization problem, and define that to be E of chi.
I mean, what's the guarantee like that for some very small chi? We just don't see like a step thing, which is that we jump into.
Well, you know that this has to go monotonically down, insofar as the larger chi variational space is a strict superset of the smaller chi variational space, right? So just by the variational principle, you know the energy has to go down as you increase chi.
But does it have to go down continuously?
No,
Oh, well, I mean, chi is real. I'm sorry. I mean, chi is an integer. So I'm being a little bit schematic here. I mean, there's ticks here, so it goes down in some way like that. But we can, in a sense, we can. So you want to know like how I've drawn it as being kind of smooth curve. You want to know whether it does this or something. There is an asymptotic sense. Well. So what I can tell you is, suppose your state, the state you're looking at, is very near a critical point, so it has a large correlation length. Then there's a scaling regime in where you can actually derive what the fall off of this energy is, and it follows some power law. I mean, all bets are off if the correlation length is small compared to the lattice scale.
What about you looking at a state and then truncating a state you already know? it might be a little different if you start with DMRG and try to solve the variation and resolve this one. And then you might end up with different state at each step depending on what chi is.
Yeah. Okay, you're saying given the exact ground state, you can ask how much error do you induce by truncating it? Yeah. Now it's true that just taking the exact ground state and truncating it this way is not the same as what DMRG would do, but I think the difference between them is at higher order in the error. So I think asymptotically they become the same actually. So if the error you introduce is epsilon, then the difference between DMRG and this prescription of truncating differs at order epsilon squared. So as it gets accurate, they're the same.
So I think the estimate of this is a power line of the worst case. Yeah, for a typical picture of this interface, typically these things became much faster.
Well, I think the reason I'm saying it is a power law is if you take a state of correlation length C or psi, so I'll get to this. We know the actual distribution of the entanglement eigenvalues, and they fall off as a power law, not exponentially. Okay, yeah.
But I'd say that that's a worst case that you can see in this wall.
Yeah, yeah, yeah. I imagine it's pretty typical, though. Do you think there's actually cases where it falls off exponentially?
Yeah.
I think power law is probably typical, actually. I mean, there's special cases like AKLT where it's finely tuned, and that's not true. But
And this is for just the gap 1D system?
Yes, so this behavior that E of chi, when there's a gap, does this power law like this is the gap case. So, but now the question is, what do we expect to be happening when the H is actually at a critical point?
So when you say power law, you're saying it's power law centering to some finite value, which is a gap?
Yeah, well, this finite value here is the actual ground state energy.
Right.
Yeah, so the error above the ground state energy per unit length follows a power law. So I guess I have 10 more minutes. So I'm not even nearly going to finish this, but I'll finish it in the next session. Okay, so I want to raise the question of, yeah, if you just do this variational problem in the case of a critical state, what are the properties of the sequence of matrix product states you get as you increase the bond dimension? And the beautiful thing is that there's some universality which arises. So let me say what naively I might think the answer would be, it's sort of like what you pointed out. You could think of this as a two-step process where you say, okay, imagine there's the exact ground state of the conformal field theory, and if you make some particular cut here, it's going to have an entanglement spectrum with an infinite number of eigenvalues. Now, the definition of this matrix product state variational ansatz is that I'm only allowed to keep chi of them. So what I'm going to do is start with the exact ground state with these pj's here, and then just truncate it by throwing away the small ones. Okay, so that'd be one thing you could think to do, that what the DMRG secretly is doing is just taking the exact thing and then just throwing away the large pj's and then somehow renormalizing, not shifting the relative weight between the others, but just renormalizing it to get unit norm again. But that actually can't make sense. And the reason is the following. So suppose what I do is, rather than being right at a critical point, I have a conformal field theory which is perturbed and given a very small length, a very small mass, so that there's a correlation length c, or equivalently a gap delta goes as 1 over c. So let me look at a system with a very small gap near a conformal field theory. So there's a beautiful result by Calabrese and Lefebvre where they're able to actually analytically compute what is the nature of the fall off of these entanglement eigenvalues pj. J here. And what they're able to show is they do indeed fall down. This one here is P naught, the biggest one. So the biggest eigenvalue is P naught equals delta to the C over 6, where C is the central charge. So let's just check that this makes sense. So as delta gets small and you approach the critical point, what's happening is that this spectrum here starts getting flatter and flatter and flatter, like this. So when delta is large, the first one has a lot of weight and it tends to fall off quickly. That means there's not so much entropy. And as the gap gets smaller, this whole spectrum gets flatter and flatter and flatter. The actual fall off of it goes as J to 2 square root B log P naught over Pj, where B is defined to be C over 6 log 1 over delta. It doesn't matter too much except that they actually have analytic form, and it only depends on the central charge. But the basic properties is that the dominant one here scales as a power law with the gap. And if you look at the asymptotics of how this falls off, it falls off as a power law.
And this is an exact result for?
So what they're able to do, so the way they get this would be, I told you the form of these Renyi entropies. So you could ask about the inverse problem given, so the Renyi entropies are computing Pj of n. So it's kind of an inverse problem where this you know from the CFT, and you can try and do an inverse transform to get what the density of what the spectrum of this is. There is a little bit of an approximation they make when they do this, but all the numerical studies seem to agree with this. Probably something like this P naught one really is exactly true because it takes just the form of a scaling law. Okay, so let's go back to this naive ansatz I made, which was what the matrix product state's going to do if you start at a critical point is take the exact ground state and then just keep the chi most important eigenvalues. But you can see in a sense that doesn't make sense, because what you're doing here, when you fix a chi, you're like putting a screen here, the particular chi, and you're keeping these ones and throwing out the rest. Now, if this is falling off quickly, like in a gap state, the amount of error you make is just the integrated weight on the states above here, which is going to be bounded. But as you approach the critical point, this is getting very, very flat. And for any fixed chi, all the weight is actually to the right, because this P0 is going to 0. So if you do a truncation like this, you actually end up with a state completely orthogonal to the ground state, not even an approximation of it. So that can't be what the DMRG is actually doing. It needs to be doing something else. So here's the idea from Pullman et al.
Can I ask why
Yeah.
you want to do DMRG for critical system? Because there's like, Mira works well for critical system. There are other methods.
Yeah, so let's consider, well, okay, suppose you can't do Monte Carlo or something and just exact diagonalization, you can't enter the scaling regime within. So at least what I would think you'd have is the tensor network ansatz, which is DMRG and Mera, Now, Mera is this, it's a hierarchical structure which is beautifully made for CFTs. It will almost exactly capture the CFT. But you can ask, how much time does it take to find the ground state within the Mera approximation? So in Mera also introduces some sort of truncation error, like you can't exactly do it. There's also a bond dimension chi. I don't exactly remember what the state of the art is, but it's like chi is somewhere between, the computational time goes as some very high power law, like chi goes to somewhere between 6 and 9. So I said DMRG goes as order chi cubed. Now this a priori doesn't tell you anything because you need to know how much more quickly does the accuracy of Mera extract critical exponents than this one. So there's only really one or maybe two people in the world who really have like state-of-the-art Mera, and they actually put out a table where they compared doing finite entanglement scaling versus Mera to get the accuracy of something. Now the accuracy indeed scales much more quickly for Mera than chi, but if you instead do accuracy versus time, they're about the same. I think the DMRG was maybe even slightly faster. So the basic answer to your question is that like Mera is very, very beautiful, but it's actually quite tricky to implement, and not obviously like exponentially faster. Though Mera does make it easier to extract kind of all the critical properties all at once because of the structure it has. Whereas for doing DMRG, it's more like standard finite size scaling.
The answer was not a lot of people know how to use Mera, or?
Yeah. DMRG, it's just very easy to get the equivalent of a state-of-the-art code. And Mera, I don't think that's the case at the moment. Maybe, I mean, that's like an implementation issue. So maybe that's up to debate how hard it is. Yeah, that's all I'll say on that. Okay, so let's just say that we did put in the critical Hamiltonian, you just run DMRG. And when you minimize the energy, you get this state chi. So we want to ask what are the scaling, what are the properties of this chi. Now, one thing I should tell you about matrix product states that actually follows from this definition I've given you is that no matter what matrix product state you have, if you compute a correlation function, so some O1 x O2. So let's say you look at a correlation function, and implicitly I'm looking at the connected component. And you can ask, how does this scale as you bring the 2 points very far apart? Then from the structure of the matrix product states, asymptotically, these are always bounded by some number 1, 2, e to the negative x over c. In other words, all correlations decay exponentially. And the important thing is that this bound, the correlation length is the same no matter what operators 1 and 2 you put. So in other words, like the matrix product state has a upper bound on correlations. And computing this correlation length given the matrix product state is a very standard thing to do that one could look up. So it's going to be very natural to ask about what was the correlation length I got from the matrix product state when you did the DMRG at bond dimension chi. And what I'm going to call this is, this correlation length is not the physical correlation length of the state. I'm at a critical point, so C is actually infinite. So I'm going to give this a subscript here, FE, finite entanglement. This is a correlation length induced by the fact that DMRG can only capture a finite amount of entanglement. So Frank and the others called this the finite entanglement correlation length. And equivalently, I could define just by dimensional analysis a finite entanglement gap defined to be the scale as 1 over. So conceptually, it's as if by doing DMRG, the DMRG introduced a gap into the system. So you can think of it as the DMRG is almost like studying the critical point perturbed by some relevant perturbation which opened up a gap. So the ansatz they made was that all the properties of the variational state you get chi behave just as if there was a gap introduced into the system which induces correlation length C, finite entanglement. So should I just continue at the next lecture?
If you can hold 5, 10 minutes.
Okay. I'll try and.
Maximum 10.
So now the question will be, what do we think the form of C is as a function of chi, for instance? So the gist of the argument is as follows. Rather than the one-step process I mentioned before, which was take the exact ground state of the CFT and then truncate it to finite bond dimension, the idea is the following. Their claim is that the output of the DMRG is of the following form. You start with the exact ground state, if there was a gap, of delta. Then you take that state and you truncate by throwing away the low-lying entanglement eigenvalues down to bond dimension chi. Okay, and then what you do is the output. Okay, so let me clarify my notation once more. This delta is the actual ground state as if there was a gap delta. That generically will have an infinite number of entanglement eigenvalues that fell off with that power law form. Okay, step 2 is you take that exact ground state, and then on any bond, you just throw away all the low-lying entanglement values, keeping the chi most important of them. So this thing is now a matrix product state approximation to a gap ground state. Now, their claim is that this state here, chi, is the output of the DMRG when running it on a critical Hamiltonian. And their claim is that this comes from minimizing over all choices of the gap. And I should say this gap here is going to be exactly the finite entanglement gap. So this is a kind of cool idea. They say the output of the DMRG comes from taking this process and then minimizing over all choices of gap for what the energy of the state is.
What do you mean by choice of gap?
Say that again?
What do you mean by choice of gap?
Well, okay, so actually, let me not call this. So you could introduce a perturbation into the CFT and get a gap delta, and then truncate it to get this state delta chi. Now, treat this as a variational problem, where this is a set of variational states parameterized by delta and chi. And you can ask, if I'm trying to use this variational space to approximate the ground state of the CFT, then what you'd want to do is minimize over this variational parameter, which was the gap.
But in whatever direction that I choose to perturb, won't I be able to change the degree to which I'm introducing the perturbation to make that 0 to tune into the critical point, right?
Yeah, so here's what happens though. So let me say why there's a trade-off here, because there's a trade-off. So by choosing a finite delta here, your starting point introduces some energy in the error above the actual ground state of the CFT. But there's another error that you introduce here by truncating it into matrix product state form. And if you have a state with a very small gap, the energy here is good, but the truncation becomes very severe. So you induce an energy error here. So there's a trade-off between a good starting point and the amount of damage you do by truncating it to a matrix product state. And it's exactly the trade-off between these two which leads to, yeah, so if you just call this thing E of delta chi, and look at delta, it's going to end up having some minimum here. And let's say this was at chi equals 10. If you do it at larger bond dimension, let's say this one's chi equals 20. The error from this is I will get into this. The error becomes less severe, and the optimal delta comes in. Yeah. So yeah. Mm-hmm.
The statement is the last, the chi that you get, the state chi that you get is what? What is that?
The statement is that effectively all the scaling properties of this behave as if it was followed from this definition. So in particular, what we're going to find is when we solve this minimization problem, so I minimize overall gaps here, and that's going to define, when you solve this minimalization problem, some FE of chi. That was what was the delta that minimized this given chi. And the claim is that and likewise from this C FE equals 1 over delta FE. So from this argument, we're going to derive a particular form of this. And the claim is that the DMRG will, the correlation length will obey the same form.
Can I think of this as a free energy? Like now I'm not minimizing the energy, but I'm minimizing energy with respect to entropy as well.
Why do you say oh. But it would be like an entanglement free entropy? Oh, that's a good question. I need to think about that. That might be true. That'd be a little bit more as if you're putting kind of a soft cutoff. Like you're like smoothly penalizing high entropy. The details here, it kind of matters that you're just putting on a hard cutoff, so I don't immediately know the answer. Okay, so what I want to outline is what the form of this energy is. So the idea is it's going to be the ground state of the energy of the CFT, and then it's going to introduce two costs. So this energy E of delta chi has three terms. First, it's the true ground state energy of the CFT. That's the first term. Now, the next term comes from the fact that I'm trying to approximate the ground state by adding this fictitious gap that isn't really there. And you can ask, what is the ground state energy? What is the energy introduced, the energy density introduced by approximating the ground state of the CFT by a gapped one? And that's actually known to take the form A delta squared. There's a scaling argument for that. So that's the energy introduced here. And then there's a second energy cost I'm going to get by truncating this state. So the way you would calculate that is follows. I have this spectrum delta, which had this fall off like this. So the exact gap ground state has an infinite number of entanglement eigenvalues, and I'm trying to approximate it by this state delta chi is equal to sum of j equals 1 to chi. So I sort of mock up by what an MPS does is you just throw away the small entanglement eigenvalues, but then you need to renormalize the state p where, sorry, this is square root p, where p is the sum of j equals 1 to chi of pj. So if you were to keep all the states, this p eventually saturates to 1, but by truncating it, you change the norm of the state. So you need to renormalize it by p. Now, I'm not going to derive the form of this, but because from this result of Calabrese, we actually know the asymptotic form of how the pj's fall off. The point is that behavior of this probability here depends only on the central charge, the gap, and the number of states you keep, and this takes some universal form which is known. So this thing is known. Okay, so now the idea is when you do this truncation, you further increase the ground state energy because you're not even exactly using this state. And the idea is that if you imagine that if you think about truncating it as introducing some excited states of the state with a gap here, you can just roughly estimate that the energy you introduce, we'll just assume all those excited states have an energy density comparable to the gap. That's going to induce a further energy B times 1 minus PC delta chi. So in other words, when P is 1, that meant chi was very large and you didn't do any truncation, then this error here goes to 0. But when P is small, there's some error here, and that introduces on the order of a gap of energy for however much you had to screw up the state by truncating it. Okay, I'm done, but the point is that these two terms, this one grows with delta, but if you look at this one shrinks with delta, so there's a trade-off between the two. And you can actually solve the minimization problem, and you get that the beautiful output to this problem is that the finite entanglement gap introduced by the bond dimension chi goes like chi to the negative kappa of c, where equals 6 over c, 1 over square root 12 over c plus 1. This really mysterious formula pops up from doing the minimization, and you find that the gap induced goes as a power law with a bond dimension that depends only on the central charge. So it's really cool. It's as if the bond dimension of DMRG behaves like a scaling operator whose dimension is given by kappa. So I can try and finish this in the next lecture, but it means that you can do infinite DMRG and treat the bond dimension as a scaling perturbation. And then any time where for usual finite size scaling you would have a size, you now have a bond dimension chi, which has known scaling dimension. Okay, so I'll stop there for now.